lecture materials. Okay, so just a quick recap about what we have talked about from week 1 to week 5 is that we introduced the idea of random variables. Okay, and then we mentioned that there are two main branches. One is the discrete case, and the other one is the continuous case. And then for the discrete random variables, we are referring to the random variable that can take any integer values like 0, 1, 2, 3, like that. And then for the continuous case, we are working with random variables or numeric value that are real values. Okay. And then we talk about their probability mass function and the probability density function. So for the discrete random variable, we use probability mass function to describe the behavior of the random variable or the distributions of the x's or the random values. And then for the continuous case, we have the probability density function. Okay, so we have some formulas or functions to describe what does the random variable or the numeric value distributed across the support. So from the integer range and also the real value. And we use the two functions to describe their distribution, their random behaviors. Okay, and then after that, we introduced one major concept is called the moments. Okay, and then we talk about the first moment, which is also the expected value, which is also the mean of those the random variable x can take. And then we also have the higher order moments, like x raised to the power of 2, and then all the way to the expectation of x raised to the power of k. So these are different moments. And then we introduce some distributions as examples, and then to calculating their moments. Okay. And then some of the distribution we talk about in a discrete case are binomial distribution and Poisson distribution. And then for the continuous case, we talk about the exponential distribution, the gamma distribution, and also the normal distribution. Okay. So we use these distributions as examples to talk about the moments that you can derive from the probability mass function or the probability density functions. And then besides using the definition of the expectation, we also introduce the idea of the moment generating function. These are just some other function that can generate the moments. Okay, so it's just another way to calculate all these things. Okay, and yeah, so there are of course hundreds of different distributions, but all of their distributions, if you want to calculate their moments, you can, or if you want to calculate their to get their moment generating functions, you can just use the definition to get those things. So the moment generating function is defined as the m of x, which is a function of t, and then is defined as the expectation of e raised to the power of xt. And then we also mention about some properties of the moment generating function, as well as the uniqueness theorems, where you can use these things to identify what the distribution of that random variable, of the new random variable belongs to. Okay, so this is from, so up to here is everything from week 1 to week 5. Any question or thoughts up to this point? So we have just been introduced some very standard statistical concept, which is the random variables, and then their corresponding moments, and then you can also use the moment generating function to get those moments. So these are the major things that we talk about, the statistical concept. And then the rest, we're just using some mathematical tricks to derive lots of the formula. But the main concept, so these are just the main concept that we have introduced. Okay. So far we have not talked about anything about probability. So you will notice everything here is called function. So these are some functions that are related to these random variables that have some random phenomena that you can use these functions to describe all these random phenomena. Okay. But now, so starting on Tuesday and also today, we will talk about the idea of the probability. Yeah. So now, after we have a good handle on those functions and the random variables, now we are ready to talk about the probabilities. Okay. Yeah. And that is also what we have started to do on Tuesday. And now we're talking about the probabilities that you can give a number between 0 and 1 to say how likely something is going to happen. But all these will need to come after we have a good handle on how we know how to work with random variables and also their moment generating function. And later, and also on Tuesday, we already showed that how we use the moments to relate to kind of like we invented the distribution from scratch, and then we introduced the idea by using coin tosses to talk about probability. Yeah. So from week 1 to week 5, we're just talking about something that can be used to describe the random behavior. Now we are ready to talk about the probability of something, how likely the chance that something happens. So now we are going to talk about probabilities. Okay. Before we start, any thoughts, questions, comments before we talk about probabilities? Okay, so now let's revisit the case, so my idea is that we are going to reinvent the distributions that we have introduced before from a probability standpoint. So previously we talked about all these from a functions, mathematical tricks to identify the moments and describe some random behavior. Now we are going to revisit those distributions from a probability standpoint. Okay. So on Tuesday, we talk about coin flipping. So let's just revisit that examples. So on Tuesday, we talk about how to flip 3 coins. Okay, and then we end up with the sample space of 3 heads, and then also one scenario will be 3 tails. And then we also have the case in the middle, which is 2 heads. But the order of the heads can also be different. So we have 2 heads and 1 tail, and then 2 heads and 1 tail in this order, and then 2 heads and 1 tail in this order. And we also have the case of 1 head and 2 tail in this order, and then 2 tail and 1 head, and also 2 tail and 1 head. Okay, so by flipping 3 coins, we identify that there are 8 outcomes in the context of coin flipping. But now let's revisit the idea of the random variables, or more specifically, how to quantify the things that we are interested to measure the probability associated to these. And the probability or the random variables for this case is that we define the x to be the number of heads observed from 3 coin flip. Okay. So now we define the x in this case, and because we only have 3 coins, so that means the x can only take the value. You either observe no head, and then 1 head, and then 2 head, and then 3 heads. Okay, so this is the support or the associated value that this random variable can take. And now we are ready to talk about the probabilities for like when in these examples, like coin flipping, and what is the probability that we'll be observing 0 hat, what is the probability that we'll be observing 1 hat, and 2 and 3. Okay, yeah. So on Tuesday, we invented, or we kind of like reinvented the binomial distribution from scratch in the following way. So we're calculating that first of all, we identify the number of ways to get these. So if we have 3 coins, and then we want to get 0 hat, then we have this binomial coefficient that can count how many ways that we can get that scenario. So out of those 8 scenarios, there's only one of them satisfy the condition. And this counting mechanism will give us the number of cases out of the 8 outcomes, how many of them satisfy that there are 0. And then if we plug in the formula, which is 3 factorial over 0 factorial, and then 0 minus 3 minus 0 factorial, you will get 1 way. And this is related or associated to the case when there are 0 hat, which is the 3-tail case. Okay, so let me just put it here. So there are only 1 way out of those 8 outcomes that you can get. So that is one of the measure that you can quantify from those 8 outcomes in this 3 coin flipping case. How many of them satisfy the thing that we want to calculate? In our case, is x is equal to 0 hat. So there are only 1 way. Okay. Similarly, for out of 3 coin tosses to get 3 hat, we will also have exactly 1 way to get that, which is associated to the hat, and hat case. Okay, so based on the table, we notice that there are only 1 way, and this counting mechanism gives us the ways from out of those 8 outcomes, how many of them are related to the things that we are interested to measure in terms of the probability. Okay. And then we also have the case for 3 choose 1, which is we want to measure the probability, how many, what is the probability that flipping 3 coins, we have 1 hat, and that counting mechanism will give us the way. So by looking at the table, we already know that there should be 3. So let's see if we are able to count that there are 3 ways. So we will have 1 factorial and then 3 minus 1 factorial. So this will give you 6 divided by 2, then you will have 3 ways. Based on the table, this is the hat, tail, and then the tail, hat, and tail, and also this case. Okay, so there are 3 ways from the table if we just write down all the possible cases, and then this counting mechanism will give us 3 ways. And then similarly for the last scenario, (3 minus 2 factorial), this will also be 3 ways. And this is related to the hat, tail, hat, tail, hat, and then tail, hat. So there are also 3 ways. So in total, when we're flipping 3 coins, there are 8 total possibility or 8 outcomes in our tables. But when we're talking about the probabilities, we need to define the random variable x. This is the probability probability of some events that we are interested, and then we define x as the number of the head that we observe from the 3 points, and then we will have these possible outcomes in our random variables, and then we use the counting way to handle that. And then like last time we did is that when we now talking about the probability that can take, we are interested in the probability that there are either 0 head, 1 head, 2 head, or 3 head, then we have invented this binomial distribution in the following density function. Okay. So in this formula, to understand this formula intuitively is that the first binomial coefficient is to handle the case or the counting part when we reduce the actual coin outcomes into our random variables that we can get the number of heads. So that's the first term we'll handle. And then the P here is related to the probability. So here, this lowercase p is equal to the probability of landing on head for 1 coin. Okay. So if you are in the outcomes that you will have 2 head and 1 tail, then when you plug into this probability mass function, then you will have k equal to 2, then you essentially have the probability of so the second term and the third term, you will get the p multiplied by p multiplied by 1 minus p. So this will give you the first coin, you will get 1 tail, 1 head, also another 1 head and another tail. And then, so this will give you the probability of flipping 3 coins that satisfy 2 head and 1 tail. But then you will also have 3 different outcomes, and that will be taken care by the counting measures. So this is so we kind of like invented the binomial probability mass function from the coin tossing case. Yeah. So the probability only makes sense when you have a good handle on all the things that we talk about from week 1 to week 5. We talk about the measures, how to measure, quantify, or work with the density functions, the functions that you can describe the random variables. After we have a good handle on that, then when we go into the probability case, then we can use those ideas to talk about probability. So in the discrete case, the probability for the things x that you want to measure that equal to something is exactly the outcome from the probability mass function. Okay. So the probability mass function and the probability density function is just some functions that to describe the behavior of that random variable x. And now to talk about the probabilities of something, of some events, then we borrow the idea of the probability mass function and the probability density functions to calculate the probability of some events. And in our case, in this example, is that we are interested in the probability for observing k head out of the 3 coin flip. So in this case, the probability of some x equal to k, where k can be the number of heads, and that is exactly when you plug in k to the probability mass function, and that thing will give you the probability. Okay, so now let's also see some examples for that. Or any question up to this point? So we kind of like invented the binomial. Yeah.
You talked about the discrete case probability being the outcome from the probability mass function.
Yes.
What would it be for the continuous?
We will talk about that later. Yeah. So, yeah. Does it? Yeah. Yeah.
So this is only applicable in cases of two outcomes.
No, it can be different outcomes. So here we have three outcomes. We have what do you mean by outcomes? So yeah, we need to define. Yeah.
Flip for like per instance two outcomes.
Yeah. So in this particular examples, we are interested in the outcome that they can take 4 different outcomes. So here we define x is the number of heads, and that x can take. So out of 3 coin flip, you can get 0 head, 1 head, 2 head, and 3 heads. Yeah. And then to measure the probability of this particular event, we go back to the probability mass function, and then we mention that the probability of that is just the outcome from the mass function. So the outcome are 4 outcomes: 0, 1, 2, and 3.
Understood that point, but where I'm thinking of is the because the last part of the PMF is 1 minus p to the power of n minus x. So that seems to me to be accounting saying if this outcome does not happen, there is only one other outcome possible, and that is Is that the case?
Yes. So if
For
you
instance.
so this probability mass function that we just kind of invented right here is to measure the x equal that you can get 0 and 1, 2, and 3. And then in your case, in that part, it will be described by this part. So this is the probability for one of the head landing on head. Yeah.
Right.
And then if you want k of them, that means you need to raise the power of k. Like you have 3 coin flips, you have let's say 0.3 on landing on head, multiplied by 0.3, and then multiplied by 1 minus 0.3, which is 0.7.
Right.
Then this will give you the probability of one particular case from these 8 outcomes that you have 2 head and 1 tail. Yeah. But when we list all the table, we notice that there are 3 outcomes from this table that satisfy that. And then you will need to introduce this additional counting factor to handle the case where when you want to describe x equal to 1, 2, and 3. Yeah. So what you describe will be taken care of by this part. But when we talk about multiple coins, from this table, we're recognizing there are 3 cases that are satisfying that 2 coins on 1 tail. And then you will need to give an extra factor to handle that. And then this whole probability mass function will give us the probability that x equal to 1, 2, 3, 4. Or 0, 1, 2, and 3. Yeah. So the probability, so now we are ready to talk about probabilities once we have a good handle on those density and mass functions. And then in the discrete case, the probability of this string interval x equal to 0, 1, 2, and 3 will be exactly the outcome from the probability mass function. Yeah. And later we'll talk about the continuous case, which is no longer this. But to talk about probability, we first need to get very familiar with all those density functions and the probability mass function and also the moments. And I will also talk about how the moments will give us or would help us to derive other distributions and lead to probabilities. Yeah. So far from week 1 to week 5, we just talked about how to handle functions. And now we are ready to talk about probability. And these probability are all coming from those functions that we introduce, that we play with from week 1 to week 5. But without all those functions and all the expect moments, we are not ready to talk about. So now we are ready to talk about the probabilities. Yeah, good question. Any other question or comments? Okay, so now let's see one examples to calculating the probability of something. Okay. So here we have an example that a factory produces microchips. And then each chip is defective with probability equal to 0.08. Okay, and now a quality inspector checks 20 chips. Now we are interested in the probability of the following things. Okay, so now we might ask, what is the probability at most 2 chips are defective? Okay, so now by looking at this particular examples and then thinking about what are, and we can draw the connection or to see which of the probability density mass function we can use. So far we only talk about, like, we kind of like invented the binomial. So of course this example is we should choose the binomial case. But the intuition is that here we have some information regarding each chip is defective with a probability of 0.08. So we also have a case, we also have kind of the idea that the chip is not defective by 1 minus 0.08. So that is 0.92. So essentially, or the underlying, we are just doing a coin flip with a highly biased coin. And this coin is that we have a probability of landing on head on 0.08 and a probability of landing on tail of 0.92. And then we are also flipping 20 coins. So in this context, just checking 20 chips. So essentially just flipping 20 coins. And that gives us the hint that we are able to use the binomial distribution to model, to measure the random phenomenon here. And now we are asked about the probability that at most 2 chips. That means we are able to calculate the probability by using the probability mass function from the binomial distribution. Yeah. So up to here, we recognize the probability mass function of the binomial distribution can handle the random behavior. And now to calculate the probability, we know that the probability is just equal to the outcome from the probability mass function. So we can use the mass function to get the probability. Okay, so now we are ready to talk about probability of that. And then we are interested in the probability of at most 2 chips. So what are some scenarios that satisfy that at most 2 chips? Yeah.
0, 1, and 2?
Yes, exactly. Yeah. So we need to have the probability for x. So here, let's define x as the number of 20 chips that are defective. So, yeah. We need, and then we are interested in the probability of at most 2 chips. So that means we need to find out the probability for x equal to 0 plus the probability of x equal to 1 plus the probability of x equal to 2. And then in this case, then the sum of them will satisfy the probability that we are interested in. Okay? So this is the probability that we're interested in, and then we're also recognizing that we need to use the binomial probability mass function to calculate that. So each of the probability that x equal to something, we mentioned that the probability of that is just equal to the outcome from the probability mass function. So now let's bring in the binomial probability mass function into that to get the probability for x equal to 0, x equal to 1, x equal to 2. Okay. So now for the first term, now we notice that we identify that we need to use the binomial distribution. Then we will have 20 choosing 0. So it's like we flip 20 coins, but there are none of them landing on head. Or in our case, we check 20 chips, none of them are defective. So we are need to calculating the probability of x equal to 0, which is the outcome from the probability mass function. And by plugging the probability mass function that we just invented, have 0.08, and then 0 of them are defective. That also means we have the 1 minus 0.08 for 20 minus 0. That means we have 20 are non-defective. And when you're evaluating the outcome, so like I said here, the outcome from this probability mass function will give you the probability that x equal to 0. Okay, so if you're evaluating this probability mass function, that will give you the probability of that they're non-defective. But to answer the question or to get the probability that the thing that we are interested, we need to take the sum for all three cases to answer the question at most 2 chips. Okay, so we also need the second term, the x equal to 1 probability and the x equal to 2 probability. So maybe let me put it here. So again, using the probability mass function, we will have 20 coin or 20 chips. We need one of them are landing on head or one of them are defective. 0.08 is the probability that 1 chips are defective. We need exactly one of them, so we put a power on top, and then 1 minus 0.08. 20 minus 1, so we need 19 of them are non-defective, so we have raised the power of 19. Similarly, we have 20 chips, we want 2 of them, so exactly 2 of them are defective. The probability for 2 of them defective are 0.08 raised to the power of 2, 1 minus 0.08, 20 minus 2. Okay, so now if you plug in the k for 0 and 1 and 2 in the probability mass function, you will get the probability that you get exactly 0, exactly 1, exactly 2. When you sum them together, you can answer the question, what is the probability that at most 2 of them are defective out of your 20 chips? So if you plug in the calculator, you will get, I think it's about 0.1887 plus 0.3281 plus 0.2718. And this is equal to the probability of 0.7886. Okay, so that will be the number when you plug in to the probability mass function to get the probability. Okay, yeah, so again, for the discrete case, the probability mass function, when you're evaluating the outcome, will give you the probability that is equal to the exactly like 0, 1, or k. Yeah.
I'm sorry, Professor.
I might have a type. Yeah, is there my number wrong?
I don't know, but I got 3.2.
I don't think that would be a number for probability, right? So it should be between 0 and 1.
Oh, it doesn't count 3%.
Yeah. Okay. Yeah. So, yeah, that may be due to the issue that I also mentioned about last time. But I will talk more about that. So that might be coming from the floating issue that I talk about on Tuesday. So I would then talk about how people manage when we have that kind of issue, how people invented the binomial distribution to the Poisson distribution, like what we did on Tuesday. I will talk more about the evolution from binomial to Poisson, yeah, from a probability standpoint. So previously, when we went to week 5, we talked about the density functions, how we describe some random behavior. Now we are talking about the probability of something, yeah. And while I will talk later, I will focus on the development from binomial to Poisson. Yeah. So it should be the number. I think this should be the number, yeah. So my question here, a follow-up question is that, is this probability relatively large or small to you? Quite large, right? So if you have 20 chips, each of them have a probability of defective 0.08. When you're calculating at most 2 of them are defective out of 20, you get a number of 0.7886. So we think this would be quite a large number. But does it make sense, or is it intuitive or not? That would be a follow-up question. So now let's think about the idea of the expectation. Okay, So back then, we derived the expectation of a binomial distribution, E of x. If you look up your notes, or is equal to n multiplied by p, okay? And now, in our case, the binomial, the n is 20 chips, and then the probability for each of them is 0.08 defective. In this case, this is equal to about 1.6. So that is saying, on average or on long term, you are expected to have 1.6 chips are defective. So the question is asking for at most 2 chips. So the expectation here give you an intuition that on long run, we are already expected to have the chips. 1.6 of them are defective. So that is the thing that will happen in long run or expected. So when we're looking at this probability, which is quite large, that is also not counterintuitive because we are expected to have 1.6 of them are defective, and that probability kind of also verified, or they verified each other in some sense. So it gives us a sanity check, the expectation give us a sanity check on the defective and also on that probability, which we think is quite large in this case. Yeah. So the expectation also give you a sense of how your random behavior, what is the random phenomenon. So again, all of these probability or random behavior is deriving from the probability density function. And then once you have a good handle of that, you can have a sanity check of verifying what are the random phenomena for the behavior. In our case, is that x equal to 0, 1, 2, 3, or all the way, it could also all the way to 20. Yeah. Question?
So if we were to do the problem but expect to have 1.6 chips be defective, would the probability be closer to 1 instead of like 0.7886? Would it be closer to 1 if the value be expected?
So in that case, so the probability that is equal to getting close to 1 will be the case when you have at most okay, so to have an intuition on how we get closer to 1 is that you can make the plot like what we did on Tuesday. So on Tuesday, when we do the 3-coin examples, we make a plot for the probability that 0, 1, 2, and 3, and then I think back. Let me revisit my notes from here. I think if I plot, yeah, about this, yeah. So this is the probability for the case for x equal to 0, x equal to 1, x equal to 2 for 3 coins. So if you plot the similar plot for the 20 case, so that you will have a very, very long list. You have 0, 1, 2, all the way to 19. And then you can see that the probability when it's greater than the expected value, 1.6, let's say 2, will sharply decrease to very low value. Yeah. So the case that you will get something that is close to 1 is that you will have to have at most like a very large, like 18 of them are defective, 19 of them are defective, then you will get a probability when you sum them together will get a very close to 1. So to answer your question, you can do an exercise to plot this graph, but for 20 of them. But then you will have a very, very long of those. You will also need to calculate all those probability for that. That is a very, very long number. So you need to sum all of them, and then you will see you will get to close to 1.
I just wanted to elaborate on the problem. So this is just the problem of how will there be defective chips? Like how
the probability.
Right. Yeah. And so if we factor in that the QA person is checking 2 out of 10, right? Would we just divide this probability we got 0.788 by 10?
No, that is already the probability that answered this question. So the probability of at most 2 chips. That is just
20. Shoot, sorry.
That is the probability answering that question. Yeah.
Sorry.
But that probability is coming from the probability mass function. Yeah. So now let me ask a follow-up question. This is one like inspector checking from 20 chips. Okay, what if the same inspector not only check 20 chips from, let's say from machine 1, also checking 30 chips from machine 2. They all have the probability of defective 0.08. How should we handle this kind of? And then we want that the total of them have at most 2 defective. What would be the, yeah?
Machine 1 and 2 only produce these number of chips, right? We're not.
No, we are picking 20 of them to check. We're picking 30 of them to check. Each of the chips will have a probability, like a coin flip, landing on head 0.08. In this context, defective 0.08. We check 20 chips from the machine 1, 30 chips from machine 2. What is the probability? At most, 2 chips are defective out of those 50. The 50 chips that we check. Okay.
Can I see my answer?
No. Yeah. So let's. What is your idea on how to handle this? Yeah.
We just treat it as a total of 50 because what's important here is the defection rate. Which machine it comes from would only matter if they had different defect rates, but since they're the same, we can functionally treat it as a pool of 50
Sure.
rather than 2 pools of 22.
Yeah. So let me, yeah, exactly. And thanks for the answer. And then let me just restate your answer in a different way. So we're recognizing that when we solving the probability of at most 2 from the first machine, by identifying that we need to use the binomial probability mass function. And then for the second examples, we also have another machine coming up, and that also having the probability each of the chips are defective 0.08. But that is saying the other one is also following, we can also use a binomial probability mass function to describe the random behavior of that, right? Okay, so now we have 2 binomial random variables. Now let's revisit the moment generating function of the binomial. I think this one we also have, we have also derived the case for the sum of that. So here, let's restate the x is the number of defective in M1, machine 1. Okay, now let's introduce another variable. Is the number of defective in M2. Okay, each of them following a binomial distribution. Okay, so if you revisit previous notes, we mentioned we derive the moment generating function of x plus y. Maybe let me just look up, or just to either in week 10, when we're introducing the property of the moment generating function, we notice the binomial maybe from Tuesday. Okay, so it seems like we haven't talked about that, but then we can derive it from here. Okay, so the idea is that we're recognizing x is following a binomial, y is also following a binomial. then to identify the sum of the two random variable, of the two binomial random variables, we need to revisit the moment generating function again. We need to use the moment generating function to identify what is the underlying probability mass function that is associated to x plus y. Once we have the probability mass function, we are then able to talk about the probability. So now we go back to the case where we have the probability, the moment generating function for binomial. Have I not talked about that before? Okay, so then you should have the solution. Okay, so maybe let me just write down the thing. Okay, so if you calculate the moment generating function to identify the moment generating function of that sum, you will have the moment generating function of that sum of the two binomial should be equal to, yeah. So you can do this as an exercise, and then to get the binomial, okay, here, yeah. So if you do the moment generating function by using the property that we introduced last week, you will notice that the sum of them also following a binomial distribution with n1 plus n2 equal, and then the probability of p. So this is the probability that the one chip are defective, and this is the 20 case plus 30 chips that we check. So that is exactly what you were saying, intuitively. But the underlying, or to prove that rigorously, you need to go through the moment generating function, using the property of those to identify the density function. So you need to use them, you name the theorem to identify, first of all, it's a binomial when you take the sum to a binomial. The parameter becomes n1 plus n2, 20 chips and 30 chips. You are checking all 50 chips. And the probability for each of them defective stays 0.08. So you need to use the moment generating function, identify that, and then you will get the density probability mass function for the x and y. After you have all those information, then you can talk about the probability for the question that I asked here. What is the probability that two chips are defective if I check 20 chips from machine 1, 30 chips from machine 2, each of them has 0.08. So you need all those things from week 1 to week 5 to answer to identify the density function first. Identify the new parameter, n1 plus n2 and p, and then now we are ready to talk about the probability in this case. Yeah.
So if n1, if the probabilities for machine 1 and machine 2 are separate, like one was like 0.05 and the other 0.05.
You need to derive the density. You need to derive that would not be a binomial case.
What, couldn't you weigh the average, like have an average?
You need to check the moment generating function to get those. I don't know whether it's weighted or not, or what is the new parameter. You need to use moment generating function to check. Yeah, but I don't think it's that simple. If they are slightly different. So yeah, let me. I also don't know the answer. So you need the tool I already provided you. You need to check on your own, and let me just see. P1, P2. I don't think it's binomial anymore. If the probability 0.08 and 0, the other one is different, right? Then I don't think it's binomial. Then you will need to use the moment generating function to proceed from there, and that question will be slightly difficult. Yeah. You will not have this very simple textbook example. In this case, it's because we're just, as an illustration, we'll get that density function, mass function very easily, and then we can talk about probability. So in that case, when you just change the number, it could be very different. Yeah. But the idea is, the procedure is that use the moment generating function to check the probability mass function for the things that you are interested in. Once you get those, when you have the corresponding probability mass function or the density function for the continuous case, you can then talk about probability. Otherwise, the probability doesn't make sense. There's no foundation to talk about the probability in that sense. Yeah. Okay.
If you ask us a question like this on the exam, like, do we have to first prove that a sum follows that distribution?
You can use this so this is kind of, we already derived them, so you can use it. But if something that is new, or you don't know what the moment function is, you need to derive from scratch to understand. Yeah. But the tool or the definition, we already talked about it. It's just the same procedure. You just need to derive it first. Identify what it is from the unique theorem, and then proceed from there. Yeah. But if you know it's just N1 plus N2 and P, you can just directly use it. Yeah. The thing for the normal case, the gamma case, the binomial case, the Poisson case, we already showed it in the previous lecture. You can directly plug in when we ask the probability question. Yeah. Yeah. But everything about probability is related to the density function and the mass function. Yeah. So you need to get a good handle on those and how to. So the key part to me is that how you can manipulate the moment-generating function to identify the distribution. Once you identify that, then the probability just, for discrete case, is the outcome of the probability mass function. But you need to know what is that mass function. So that is the tricky part. The probability, just plug in a number. Yeah. Okay. So, okay. So maybe you can continue this question. Once we identify this is the binomial of 50 and a 0.8, to answer that, so again, you need x plus y equal to 0 plus the probability of x plus y equal to 1 plus the probability of x plus y equal to 2. And then again, using the binomial mass function, 50, choose 0, 0.08 raised to the power of 0, 1 minus 0.08, 50 minus 0, plus the case for 50, choosing one of them are defective, 0.01 and 0.08 and then 1 defective, 1 minus that, 49 non-defective, plus 50 of them, choose exactly two of them are defective, 0.08, 2 are defective, 48 of them are non-defective. Okay, so again, the key part is that you need to know is the binomial mass function. And then the probability that exactly 0, 1, and 2 is just the outcome from the mass function. And then sum the case for 0, 1, and 2 to answer the question that you have at most 2 for defective. Yeah. Okay. We might not be able to have to talk about the probability of a continuous case today. I still want to talk about the Poisson, how we develop from Poisson. I think that's a very important thing. Any question up to this point? So if you're interested, you can try to check what is the moment-generating function when the number are different and when the probability are different. Do you still get binomial or not? I don't have the answer, but to me, without doing calculation or doing calculation in my head, I think that is not a binomial anymore. Then you will not be able to answer the probability question very easily. But you need to use the tool, the moment-generating function, to check and then to answer the probability question in that case. When you change something, just change one thing, things can get very difficult. But you have the tool to handle those situations, which is moment-generating function. So moment-generating function is a very important tool to handle the subsequent analysis, which is in our case is the probability. There are other things that we can talk about, but right now or in this class is about now we are talking about the probability. Okay, so I still want to talk about the Poisson. So maybe I will talk about the probability of continuous things next. And also just a hint is that for probability continuous random variable, it's no longer the outcome from the probability density function. You need to do additional steps, which is integral. You probably already know, which is you need to integrate something to get the probability for continuous random variable. But we'll talk about that maybe next lecture. Okay, so I still want to talk about the Poisson progression. So last time on Tuesday, we also mentioned that there in the history, so let me write down the issue that we run into on Tuesday again. So let's say there are 10,000. I'll just use coin flip. Okay, 10,000 coins. Each landing on head with probability 0.003. Okay. And if we are interested in what is the probability that of exactly 2 head. Okay. So again, we will need to use binomial to handle that. We will need to first the probability. So the probability is just the outcome from the probability mass function. So we're going to use the probability mass function. We're interested in x equal to 2. So out of the 10,000 coin flip, we want exactly 2 head. And then we use the binomial probability mass function. We have 10,000 choosing 2. 0.003 03 raised to the power of 2, 1 minus 9998. Okay, so back then when there's no computer or calculator, to evaluate this kind of, even when you have probability mass function, you want to calculate the probability of this particular events or here, it's extremely difficult to calculate a number, even it's just a products thing. When you have a number that is between 0 and 1, and then you raise the power to a very large number, you will encounter what we call a floating point issue, which is either the number is too small, you will have tons of zeros, and then in the end you will have a 0.090 of them 0 and then 1, or a very large number like 10 raised to the power of 100. If you do that in a computer, so even nowadays computers, you will get it will not display, or even it will not store. It will just say like a infinite or a very small number. But if you're still interested in the probability of this, then people come up with the idea of the Poisson distribution to handle this kind of problem. Okay. So on Tuesday, we just briefly touch upon on how they use the Poisson distribution. And then again, when we talk about when we derive the moments, the first order moments for the Poisson distribution, we're recognizing the expectation is the lambda. Okay, so the lambda is actually just the mean of the Poisson random variable. And also for the binomial case, the mean is n multiplied by p, okay, the one that we just showed. So what people did when they using Poisson to approximate that is that they use the parameter lambda, which is the expectation, the first moment for the Poisson random variable, they use the expectation of the binomial to replace or to plug in to the expectation for the Poisson. So on Tuesday, we mentioned that in this case, the expectation on the binomial random variable is 10,000 multiplied by 0.003, which is just 3. And then we plug this into the lambda, which is the expectation for the Poisson random variable. Okay, and then if you check your notes from Tuesday, you will see that if you use the Poisson distribution to approximate this problem, we will get a relatively close number. So we will get a very good approximation for that. So back then when there's no computer, if this is very difficult to handle, people come up with the Poisson distribution to calculate the probability for that. Okay. So here I just want to, I want to give more of a derivation, but I'm not sure if you are interested or not. So maybe I'll just ask here, if you guys are interested how to see a progression from binomial to Poisson, I can talk. So, yeah, can I also get a show of hand? Okay, then I'll go over that. So it will also be some there. So I'm slightly afraid on providing too much. Okay, so now let's take a look at how to progress from binomial to Poisson. Okay, so we are revisiting the idea again, but now from a probability standpoint. Okay, so one idea or one intuition that you can get from is that let's consider the following thing. Okay. So just to provide more context here is that okay. Suppose some request arrive randomly to a center. So it's kind of like a request or a ticket for some service. Arrive randomly to a center. Arrive randomly to a, let's say, a call center. At an average rate of 5. Okay. And our goal is that we want to model the number of requests in the next minute. Okay, so now we have a more concrete problem. We can think about intuitively how to handle this case. So one idea here is that in the next minute, so let's construct a list here, and then we break these into 60 evenly spaced. Okay. So there, in this 1 minute or 60 seconds, we will receiving 5 different requests in this 1 minute time step. So we might not receive a request on the first second or the second second. We might receive a 1 on the third seconds and 0, another 1, 0, 0, and then maybe another 1 here, 1 and 0. Okay, so when we looking the problem in this particular perspective, breaking 1 minute into 60 seconds and then count at which second we receive a request, we essentially just converting this problem back into a binomial random variable. It's kind of like you flipping a coin on the first location, you get a 0. You flip a second coin on the second location, you get a 0. You flip a third coin, you get a 1, landing on head. You flip the fourth location, you get a 0, or landing on tail. So we essentially just converting this in the idea or from the perspective of coin flip, 60 coin flip again. And then each location is like landing on head and tail.
In this scenario, is 0 just no requests and then 1 is some requests?
Yeah. Or 1 in a coin flip case is like landing on head. Then we get a request landing on head. Or in a chip case, defective. So they're all just like 2 outcomes, and then we get either one or the other one. So they are just the similar thing. Yeah. But yeah. Mm-hmm.
So then the probability is like in every millisecond, like infinite period of time.
So the next idea is that I will make this 1 minute into infinite seconds, and then I will show that the binomial case will progress. Like I will calculating the limits of the binomial probability mass function. You will see when the limit of n approaching infinity, the density function will become the density function of the Poisson density function. So that is my strategy here. But let me first elaborate the setting here. There's a question.
What do you mean by like average rate of 5?
In that 1 minute, yeah.
Oh, okay.
Yeah, in that 1 minute we're getting 5. So in that 1 minute window we're getting 5 of the ones. So kind of like a Poisson setting, the average of 5 requests in that 1 minute. So eventually you will see that the average of 5 is actually just the lambda, the Poisson, the expectation of the Poisson. So by setting in this way, and then we will see how it progresses to Poisson. But right now, by looking at that, we are considering a coin flip. So right now, it's that we are flipping 60 coins. When we're thinking in this way, later I will cut this into infinite intervals. In that case, when you still do coin flipping, that will become a Poisson distribution, a Poisson random variable. So that will be the thing I will show. Okay, but right now, let's consider this from a binomial standpoint. So essentially, we will have, if we are interested in the number of requests in this minutes here, x will follow a binomial distribution where you are flipping 60 coins, and then the probability for each of them, for each of the, it just equal to 5 over 60. So you will receive 5 requests in this 60 seconds, and then the probability for each of them is just 5 over 60. So the kind of like the probability of landing on head for each of the coins is about 5 divided by 60. Okay. So now let's write this slightly different. So in a general case, okay, we will have x following a binomial with n, and then, so n is the number of coins or the number of intervals that we segregated in this 1 minute window, and p is essentially just the number, the average rate. Okay, so now let me give an average weight a letter, which is lambda. Okay, so intuitively we're just going to show how the binomial connect to Poisson. So I'm just going to use lambda, and then the lambda later will show as the binomial Poisson parameter. So I will give this average rate of 5 a letter, which is lambda. Okay, so in the general case, we are just using the probability for each coin. If we're thinking about the binomial case, it's just the number of requests, which is lambda on average, divided by the number of intervals that we segregate. Okay, then we will have a general case. And now to show that how it becomes a Poisson, I will make the n to infinity. Basically, we're just cutting the 1 minute window into a very large infinite seconds or infinite time slot, and then you will see how it becomes a Poisson. Okay, so again, starting from the probability mass function of a binomial distribution, we are interested in x equal to k. So k could, in our case, could be equal to, we want to model the number of requests. So you can define the number of requests as the k. K can be 2, 5, or up to n. Okay, so that is from the binomial perspective. And then by plugging the binomial probability mass function, we will have n choose k. So n is the number depending on how many intervals that you segregate that 1 minute. And then p is the probability for each coin landing on head. In our case, it's the lambda over n, and then raised to the power of k. And then you will have 1 minus lambda over n raised to the power of n minus k. So again, this is the binomial probability mass function. Okay. Next, I'm going to show when n goes to infinity, n choose k, so the binomial probability mass function, and let's see what does this will evolve into. Okay, so this is the quantity that I want to evaluate. So I want to segregate the 1 minute time span into infinite many segments, and let's see what the formula will evolve into. Okay. So I will write it here. So first of all, you will have the limits of the n go to infinity, and just slightly expanding the binomial coefficient. Okay. You will have lambda raised to the power of k, and then n raised to the power of k. I'm just bringing the power to the numerator and the denominator. And then for the 1 minus lambda over n raised to the power of a difference, I'm going to write it as 1 minus lambda over n raised to the power of k. I think this should be n. One minus lambda over n raised to the power of k. So the thing that the property that I use here is n a raised to the power of, maybe let me use x raised to the power of a minus b is equal to x raised to the power of a over x raised to the power of b. And you can also rewriting this as x raised to the power of a multiplied by x raised to the power of negative b. So negative b just become raising the power of b, but goes to the denominator. Okay, so this is just yeah. And that's how we end up with this equation. Okay, and okay, now we need to use another equality. So note that another equality is that the limits of n go to infinity for 1 minus lambda over n raised to the power of n, this is equal to the exponential raised to the power of negative lambda. So this is also a known equality that holds. So we are using some limits thing. You probably also see something like this in your calculus class. So this is some known equality. We are going to borrow this in our expansion. Okay, so this one always holds, and then we are going to replace this in our derivation. Okay, so the thing that goes to infinity for 1 minus lambda over n is the thing here on the numerator. So we are going to use the known equation to replace the thing on the numerator here. Okay, then continue on our expansion. Have the limits and go to infinity for these parts stay the same. Lambda raised to the power of k, n raised to the power of k, and then we will have this part replaced by that known equation, and then 1 minus lambda over n raised to the power of k. Okay, any question up to this point? Let me just pause a little bit to see if there's any yeah. It's just some expansion, and then what we did is just using that known equation to replace the numerator. Yeah. Okay. Now let's proceed. Again, we have the limits for n go to infinity. And now I'm going to cancel out the numerator for the binomial coefficient in the following way. So I'm going to cancel out this part and this part. Okay, that means we will have, on the numerator, we will have n multiplied by n minus 1 multiplied by n minus 2 all the way to n minus k plus 1. And the reason is that for anything that is n minus k and then n minus k minus 1 will all be cancelled out by the factorial in the denominator. So on the numerator, we only have that, and then in the denominator, okay. We'll have the k factorial. So the thing that I circle on the top and the denominator, they will be cancelled out, leaving only the numerator on the second one. We will have the following subsequent terms remains the same. Okay. And now let's do one more thing, then you will see how it's reduced or collapsed or evolved into a Poisson. Okay, so one last rearrangement, and go to infinity. So I'm going to write the numerator like this. And I'm going to borrow this part, this denominator, from the second term into the denominator and to the first term, and then move the k factorial to the denominator in the second term. Okay, so we will have n raised to the power of k. So I'm going to move that denominator to the denominator on the first term, move the denominator from the first term to the denominator of the second term. Multiply by lambda raised to the power of k n factorial, multiply by e raised to the power of negative lambda 1 minus that. Okay, so now we are ready to evaluate the limits. Okay, so let me make a few claims here. Okay, so this is the formulation that we are ready to evaluating the limits. And now let me point out something. So the limits for this thing here, 1 minus lambda over n raised to the power of k. When n go to infinity, what does this term equals to? Yes?
I have a question. What happened to k factorial?
Sorry, say that again?
What happened to k factorial within...
Ah, perfect. This one, right? Sorry, yeah. So what I did is that changing, okay, so let me, yeah, that's a typo. I'm changing the order here. Does that answer your question?
Yeah.
Yeah. So what I did from this line to this line is just I'm changing the things here. I'm changing the n factorial to there, but n raised to the power of k to the first denominator, k factorial to the second one. That's what I did here. Okay. So that's the formula, and that's the formulation that we are ready to evaluate the limits. Okay. So now my first claim is that the limits of this one, n go to infinity, this one will become a very large number. Rendering this fraction becomes 0. Right? If you let this fraction for n go to infinity, this fraction will be 1 or some constant divided by something very large. This will go to 0. 1 minus 0 will be equal to 1. 1 raised to the power of k will be equal to 1. So when you're evaluating this limit, this will go to 1. Okay. And then another thing is that let me see how to write, how to explain this intuitively. So this part, so that denominator will already go to 1. So now I want to say for the limits of n go to infinity, the first term here, the n minus 1 all the way to n minus k plus 1, and then n raised to the power of k. This one will also go to 1. Let me find a good intuitive way to explain this if this is not obvious. One way you can do is, you can do one, I see. Maybe this will be a good intuitive, so rewrite n minus 1 as n multiplied by 1 n. Okay, so rewrite anything n minus 1 as n multiplied by 1 minus n 1 over n. Okay, so let me elaborate a little bit. So this is what you can do. N multiply by one minus 1 over n, multiply by n of 1 minus 2 over n, all the way to n of 1 minus k plus 1 over n. Okay, so if you see that numerator in this sense, this will give you maybe n raised to the power of k, 1 minus 1 over n, 1 minus 2 over n, all the way to 1 minus k plus 1 over n. Again, when n goes to infinity, everything involving a fraction of the n will go to 0. 1 minus 0, 1 minus 0, 1 minus 0 become 1. You only have an n factor, n raised to the power of k. So I'm saying the numerator becomes n raised to the power of k. Denominator is n raised to the power of k. So this thing will converge to 1. Okay, so back to our formulation. This thing, dividing the limit, goes to 1. This thing, dividing the limit, goes to 1. All you left, this term, and this term. Okay. Now let's see what does that equal to. So from above, we started from a binomial probability mass function. When we started that question by cutting interval 1 minute into n intervals, and when we continue cutting into infinitely small intervals, then that binomial probability mass function for x equal to k will converge when n goes to infinity as lambda raised to the power of k, k factorial e raised to the power of negative lambda. And that is exactly the probability mass function of a Poisson distribution. Okay, so the idea here, when I started from the history of that, is that when you want to calculate the probability using a binomial random variable, when you have like n very large and p very small, back then when there's no calculator, you cannot do it. So the idea is that people using the average, which we already know that the expectation for the binomial is np and the expectation for the Poisson is is lambda. So we can make the change over there. And then in this example, we also show that when we flip large enough a coin, then essentially the binomial probability mass function will gradually become a Poisson probability mass function. And then from there, you will be able to, using the Poisson probability mass function, to answer a probability question that was started from the binomial probability mass function, but is not able to do it back then when you run into the floating point issue. Okay, so this is more like a, so now we are gradually talking about, okay. So now we're gradually talking about probabilities, but all the probability is based on the foundation for probability mass function, density function, and moment generating function. Once we have a good handle of those, we can now consider the same thing, similar things, again, from a probability standpoint. Yeah. Yes?
Is there a particular, amount of n that you start using for Poisson distribution?
So your question is that when to use Poisson, when to use binomial? Actually, that's a very good question. The short answer is that there isn't a good choice. It's just really depending on your preference or on your thing. So to calculating the probability, let's say the probability of x equal to 2 or the number of requests. For this example, you can either use binomial or either using the Poisson. They can all give you the probability to answer this question. Yeah. So it's kind of like up to your preference, up to your choice, which probability mass function you want to use, but they will give you different numbers. So if you believe that this thing follows binomial, then you use binomial mass function, you will get a probability. And that is the probability to answer that question. So there isn't a right way. It just, if you believe that this random, if you believe binomial can, or Poisson can, you can all get the probability that based on your choice of the mass function. But they can all answer the same question. Are you guys interested in another quick history thing or some machine learning? Okay, yeah. So last time we also mentioned about the recurrent neural network and the LSTM, the long short-term memory. That is a very great invention in the deep neural network. And the idea is that they want to use the LSTM to solve the problem of the recurrent neural network when you have the floating point issue. And another thing here is called, another machine learning model is called exponential random graph model. So this is a model that's working on graphs. Okay. So graph in mathematical sense is something that you have a vertex and then you're connecting them. So this is a graph with 5 nodes and then also 5 edges. You can using a adjacency matrix to represent a graph. You will have node 1, node 2, all the way to node 5, node 1, node 2, all the way to node 5. And here, if node 1 and node 2 has an edge, you can mark the adjacency matrix here, node 1 and node 2, as 1. That is saying node 1 and node 2 has an edge. But when the edge has a weight, so for example, let's say I have a weight of 3, and these edges have a weight of 4, this weight have a weight of 1, 2, and 1, then essentially you will have you have a weighted graph. Okay. One thing for this exponential random graph model is a machine learning model that can modeling the graph and also modeling the weights of the graph. And in the ergon framework, there's 2 things. One is the binomial reference, ergon, and then, of course, a Poisson reference, ergon. So if you want to handle graphs, or in machine learning, when you want to handle graph with weighted graph, then if you want to use the ergon framework, there are 2 options: binomial reference and Poisson reference to handle when the edges are weights, are non-integers, just like what we did here. And then again, there isn't a right choice for which one you should use, but all of them can handle the weights on edges. And this is a model to working on graphs. And graph is a very complex structure in like a Facebook network or some social network. So yeah, and then for this machine learning model, they have the binomial case and the Poisson case. Okay, so that's just some notes. If you're not interested, then don't worry about it. Yeah, that's it.